following data were obtained for a chemical reaction. A goes to B. Got some data right here. If we look from experiments 1 to 2, we can see that the concentration doubles from 2 to 1, and it remains the same here for B. And we can see that the initial rate goes from 0.8 to 1.6, so it also doubles. So if both double, we can say that concentration of A then is to the first order. This one doubles and this one doubles. Then we can take a look at 3 and 1, where A remains the same, but from 3 to 1, the concentration of B, or the moles of B, double. And then we can see it goes from 0.4 to 0.6. So mathematically, a way that you could write this down is you could say B is going to be to some power y, and that, compared with B to some power y, is going to equal the 1.6 from the first reaction to 0.4 for the second reaction. And so 16 divided by 4, or 1.6 divided by 4 is 4, and then B has to be to some power here, and this is 6 divided by 3, which is equal to 2. So 2 to some power y is equal to 4, y equals 2, or the exponent for B. So we'd say that the concentration of B is to the second power. And so if we were to write the rate law, then we were supposed to say rate is equal to K, A to the first power, B to the second power. 4.5, a similar question. In this one, we can see that iodine doesn't change from the first to the second. From the first to the second it doubles, and you can see that the rate doubles. And if you can't tell that for sure, you can do OCl minus, and we can take the second one right here, experiment 2, to experiment 1. So 3 times 10 to the negative third divided by 1.5 times 10 to the negative third. So those cancel, so 3 divided by 1, which is 2. And that's going to be to some power, we'll call it x. And that's going to equal the rate, which is 2.72 divided by 1.36, and that's to the second power as well. So 2 to some power equals 2, so x equals 1. So the concentration of OCl minus is going to be to the first power. Then we can see from 1 and 3, 3 and 1, the concentrations remain the same, and it doubles here from 1 to 3. And we can see that it does the same thing right here, 1.3 and 2.7, which was exactly the same as we have here. And so it would also be to the first power. And so I minus is also to the first power. And so the rate law would be rate is equal to K, OCl minus to the first power, I minus to the first power. They're the rate laws for both of those. Number 5. The rate of the dimerization of NO2 is observed to increase by a factor of 27 when the concentration was NO2 is tripled. So if it's tripled, that would be to some power, we'll call it x, and it equals 27 when it increased by a factor of 27. So that means it's got to be to the third power. And so it's third order, which is D. Number 5.5. The rate of the reaction was observed to increase by a factor of 2. By a factor of 2 when the concentration of A was doubled, which is the order of the reaction. So if it doubles to some power, we'll call it x, and it was seen to also double, we would say 2 to some power equals 2, so x equals 1. So that would be to the first power, B. Number 6, a first order reaction has a half-life of 30 seconds. Calculate the rate constant. So looking at the concentration versus time rate law page in first order, half-life equation, T equals the natural log of 2 divided by K. And we know that the half-life is 30 seconds. And equals 0.693 divided by k. Solving for k, we'd multiply both sides by k, divide both sides by 30, and we end up with a k. Oh, I'm sorry, it tells us that the k is 0.5. I'm sorry, the k would then equal 0.0231, and that would be per second right here after we move the k to this side. And the units on this are seconds underneath here, so 1/seconds are our units. Okay, moving on, 6.5. A first order reaction has a rate constant, so now we're given the rate constant is 0.5 seconds to the -1. Calculate the half-life, so T1/2 once again is equal to 0.693 divided by k. This time we're given k, so 0.693 divided by 0.5, and that's per second, so that's 1/second, so our units are going to be in seconds. So 0.693 divided by 0.5 ends up being 1.39 seconds. That's number 6.5. Number 7. The reaction below is first order in H2O2. The original solution is 1 molar. H2O2 is 0.25 after 50 minutes. The half-life for this reaction is blank minutes. So we could say that we started at 1 molar, and a half-life of that would be half as much, so that would be to 0.5 molar. Another half-life of that would be half as much, so 0.25. So we're told that this is 50 minutes to reach this amount. And so if we start here at 0, how much time would it take to get to this middle one right here? Well, half as much, which would be 25 minutes. So T1/2 is equal to 25 minutes. Whoops, number 7.5. A similar question. The solution is originally 0.6 molar and is 0.15 after 36 minutes. So we go to 0.15 molar. The half-life for this reaction is blank minutes. So if you go from 0.6, half of that is the half-life, so 0.3 molar. Half of that would then be another, which is 0.15. So here we have the first half-life, and here we have the second half-life. And we know that this took 36 minutes. So this must have taken half as much, so that would be 18 minutes. So our half-life, T1/2, is equal to 18 minutes. That completes number 7.5.